Good morning, honors chemistry students. The next element that I would like to examine with you as part of our review of atomic structure and quantum mechanics is the oxygen atom, which is immediately to the left of nitrogen on the way over to neon in the second row of the periodic table. To do so, I'm going to have you look at or examine an isotope of oxygen which has 8 protons and has a mass number of 16. Once again, we identify the isotope of an element by its mass number. So we would affectionately refer to this particular isotope of oxygen as Oxygen-16 to pay homage to the fact that it's got 8 protons and most likely 8 neutrons. Keep in mind that the 8 represents the atomic number, which is the Z value, which also represents the atomic number, which is equivalent to the number of protons in the atom, which should also equal the number of negatively charged electrons in a neutral atom, because the sum of the positive and negative charges should be the same, and in this case is 8. 16 is what we affectionately refer to as the A value, which is the mass number, which is equal to the sum of the protons, which are positively charged, plus the number of neutrons, which have no charge. In this case, we've already established that the number of protons is 8, and the number of neutrons can be determined by subtracting the atomic number from the mass number. And in this case, that difference is 8. So we can predict that we have 8 neutrons as well. So 8 and 8 gives a sum of 16, which is the mass number of oxygen. We say that oxygen is an element which is strategically positioned in row 2 of the periodic table, also known as period 2, because it has enough electrons to start filling the second energy level. We say it's a member of column 16, otherwise known as group 6A, because as a representative element, the A elements represent that the Roman numeral represents the number of valence electrons. So we say in this case that the designation of A means that this is a representative element, and thus the Roman numeral represents the number of valence electrons, which in this case is 6. And we say that oxygen is at the top of its column or group, so therefore we say that it is the first member of the oxygen family. That being said, I want you to once again draw the AELD representation, which in essence, we will start with a nucleus and divide that into 2 boxes, an upper box to represent the number of protons and a bottom box to represent the number of neutrons. In this case, in this particular isotope, we know there are 8 protons and 8 neutrons that comprise the nucleus. Notice that we do not say there are 8 protons and 8 neutrons in the nucleus. We are saying they are the nucleus. With that being said, we need to position or 8 electrons in the energy levels. So therefore, if we have 8 protons, we have 8 electrons that we have to position. The first 2 electrons go on the first energy level, which is the n equals 1 energy level, also known historically as the K shell. Keep in mind those first 2 electrons are s electrons on the first energy level, just like hydrogen and helium. Once the first energy level is filled with a maximum of 2 electrons, The strategy is, by the off-ball principle, to start placing electrons in the next lowest energy level available, which in this case would be the n equals 2. We place 2 to the right in keeping with our pattern, and then that's 2 of 6. We need to put 1 on top, 1 on the side, 1 on the bottom by Hund's rule before we go back and pair them up. Keep in mind that each orbital on a sublevel gets 1 electron before you pair them up, which is consistent with Hund's rule, and thus this particular isotope of oxygen has 6 valence electrons, 2 in the s, a total of 4 in the p, with 2 being paired and the other 2 electrons being unpaired. So we say that those valence electrons are located on the n equals 2 energy level. And so these are known as valence electrons. And we're going to provide a more sophisticated definition of valence electrons. Heretofore, we've said that valence electrons are the number of electrons in the highest occupied energy level. Now we're technically going to change that to the number of valence electrons in the highest occupied s and or p sublevels. So therefore, we have 6 valence electrons in oxygen, 2 of which are paired and 2 of which are unpaired. The paired electrons we are going to refer to hereinafter as lone pairs, just like Eric Carmen's song, All by Myself. They exist all by themselves, paired up. That being said, I want you once again to represent the valence electrons in an electron dot representation. And the electron dot representation includes the symbol for the element, which in this case is O, along with dots to represent the valence electrons. These 2 dots represent those 2 s electrons. Then we're going to put 1 dot in a p, another dot in a second p, a third dot in a third p, and another dot pairing up the lone p electron. So therefore, that's what your electron dot representation looks like for oxygen. And the electron dot should look something like the arrangement of electrons in the AELD. The next representation we're going to do again is the orbital notation for oxygen. And keep in mind that orbital notation is a way to represent the filling of electrons and energy levels moving from the ground state or lowest energy levels, moving away from the nucleus of an atom. By now you should recognize the first energy level has just an s sublevel which holds 2 electrons. Those 2 electrons are these 2 electrons on the first level. So we say that the first level contains a maximum of 2 electrons. And keep in mind that by the Aufbau principle, which is the German word to build up, the electron configuration is built from the ground up, placing electrons on the lowest energy levels available in an atom, and then moving away from the nucleus to higher sublevels and energy levels. So once the 1s is filled, we move to the 2s and place 2 electrons in the 2s. These 2 electrons are that lone pair of electrons, which are this lone pair of electrons. Once the s sublevel is filled, you move to the 2p sublevel. One of the 2 p's lies along the x, the y, and another along the z-axis. So we place these according to Hund's rule and say that each orbital, which holds a maximum of 2 electrons, in a sublevel gets 1 electron with similar spins before you pair them up. And so thus, you can clearly see that oxygen has 6 valence electrons, 2 in the s and 4 in the p. To write the address for these electrons, valence electrons, we use what's called the electron configuration. The electron configuration is located on the periodic table and is the address for a valence electron in an atom. In oxygen's case, we have 2 electrons in an s sublevel on the first energy level, so we would start by writing 1s2. You note that we have 2 electrons in an s sublevel on the second energy level, so you would add 2s2 as part of its address. Then move to the p sublevel, which holds a maximum of, well, actually in this case holds 4 electrons. So we would write 2p4. Notice that if you sum the superscripts, they sum to 8 valence electrons. 4 and 2 is 8. Another way one could write this is to pay homage to helium, because 1s2 is the valence electron for helium, and then add the outer configuration of oxygen, which is 2s2, 2p4. And thus, that is the electron configuration for oxygen, which is in column 6A, once again, and contains 6 valence electrons, just like every other member of the group of oxygen, which includes sulfur, selenium, tellurium, and polonium. The last representation that I would like you to include is the Cartesian coordinate system, which represents the valence electrons in an XY plane. And this is where this begins to pay dividends, because you can represent p electrons. The first energy level is visualized as orbiting around the nucleus, which is the vertex of this coordinate system, which holds 2 electrons. And we say those electrons, in terms of Bohr's theory, orbit the nucleus much the same as planets orbit the sun in discrete energy levels, which means they can only be on that level. But quantum mechanics really views this region of space as spherical, and that there's really a probabilistic distribution of these 2 electrons that can exist, have enough energy to exist anywhere within that region of space. Once the 1s is filled, we set out to fill the 2s. A little bit circle challenge there, but we'll survive. And place 2 electrons in the 2s. These 2 electrons should be those 2 electrons, which are those 2 electrons, which are those 2 electrons, which are those 2 electrons. You should at this point begin to connect the various representations and their meaning. The p orbitals are higher in energy, and we'll talk a little bit more about that, but one p orbital is dumbbell shaped and lies along the x-axis. Another one is visualized as being dumbbell shaped and lies along the y-axis. And if I can draw this z-axis to add the third dimension, another p orbital is strategically positioned theoretically along the z. To place the last 4 electrons, I would suggest you start in the x, then put 1 in the y, 1 in the z, and then pair up the 1 in the y. I do that because I want the arrangement of these electrons to look similar to the arrangement of electrons in the electron dot and the AELD. And with that, the next atom that we will look at is the noble gas neon.